In August 1994, a research icebreaker cut across the top of the world through thick, grinding ice north of the Laptov Sea. Scientists aboard lowered long metal corers through narrow openings in the floes and pulled up cylinders of seafloor mud from nearly 4 kilometers down. Each section was labeled, sealed, and stored. BC-08 from 78 degrees north, BC-17 from 81, and BC-28 from 89 near the pole. For decades, those cores sat quiet. Then, a new generation of geochemists reopened them and found a record of Arctic ice not written in fossils or shells, but in stardust. Every year, billions of microscopic grains of cosmic dust drift into Earth's atmosphere. Each carries traces of the isotope helium-3. When the Arctic Ocean is open, that dust settles to the bottom and mixes with minerals containing thorium-230, an element formed naturally in seawater. But when sea ice locks the surface, the cosmic dust never makes it through. That simple blockage turns the seafloor into a measuring device for ice itself. By comparing the ratio of thorium-230 to helium-3 across layers of sediment, the team reconstructed 30,000 years of ice history in the central Arctic, far beyond anything satellites or historical logs could show. The picture that emerged is stark. During the last glacial period, the central Arctic was sealed under thick perennial ice, tens of meters deep. At those times, helium-3 nearly vanished from the record, showing a sky cut off from the ocean below. Then, around 15,000 years ago, the balance flipped. Global temperatures rose, and the Great Polar Shield began to fracture. Dust from space surged into the cores, evidence that wide leads and melt ponds opened across the high Arctic. The timing matches the warming known as the Bowling-Allerod event, an abrupt climate shift that melted continental glaciers and raised sea levels worldwide. In the Arctic sediments, it reads as a sudden pulse of cosmic dust marking the breakup of ancient sea ice. By the early Holocene, roughly 10,000 years ago, the record shows a seasonally ice-covered ocean. Summers were largely open, winters refroze the surface. It was the warmest Arctic in the past 30 millennia, a condition the planet may revisit before 2100. Then came reversal. As solar intensity declined and northern temperatures cooled, sea ice returned. From 5,000 years ago to the present, helium-3 concentrations fell again, tracing the slow expansion of multi-year ice that explorers later described as an endless white barrier. But the story does not stop with ice alone. The same cores also preserve nitrogen isotopes from microscopic foraminifera, records of how marine life responded. When the Arctic opened, nitrogen consumption by plankton rose sharply. When it froze, biological activity collapsed. The data reveal a tight coupling between sea ice coverage and nutrient use. The thinner the ice, the more the ocean breathes and feeds its upper layers. At the pole itself, the northernmost core, BC-28, told a different tale. Even during the Great Deglacial Melt, its readings never dropped to true open water values. That site stayed under ice throughout, a small refuge of permanence at the planet's center. Together, the three cores form the longest continuous timeline of central Arctic sea ice change ever recovered. They show that ice retreat and regrowth track the rhythm of sunlight and atmosphere, not random fluctuation. And they warn that as greenhouse forcing now accelerates, the system is entering territory last seen more than 10,000 years ago. For the scientists who worked on those samples in 2025, the next step is already defined. Drilling deeper, closer to 90 degrees north, to see how far the cosmic dust signal extends. Each grain of extraterrestrial helium-3 that lands on the Arctic today will become part of that future record, locked in mud until another generation digs it out and reads how the ice finally gave way. That's the timeline written not by satellites or sensors, but by dust from space.